Okay, so I know it's been a minute. Everybody slept, everybody had a week off, but Chapter 12 is all about statistics. And we're learning different ways of stating our statistics, of understanding our statistics, of quantifying our statistics. And we spent a lot of time talking about mean, median, and mode. Those were kind of our 3 M's that we looked at that we spent quite a bit of time with. And today we're going to talk about the measures of disbursement. So measures of disbursement talk about the spread of the data. And the first way we're going to talk about that is the range. And that's kind of a general term that you will hear us use. What is the range of the data? And that's basically you're looking at what's the biggest value versus what's the littlest value. How much space is there? When you take an exam, professors always want to know what was the highest grade on the exam, what was the lowest grade on the exam, and then where did most of the students fall? Because most of the students should fall theoretically right in the C range, with A and B students being a little bit less and D and F students being a little bit less. And if the disbursement is different than that, then was that material taught well? Did the students prepare well? Like, what happened to make the disbursement off? And so that's just like a generalized example of what disbursement is used for. But range is going to look at the difference between your highest value and your lowest value. And it can tell you a lot about what the values are actually telling you. So we're going to do a couple of different examples. We're going to look at range, and then we're going to really dive into standard deviation is the main focus for 12.3. And there's lots of little steps that will get us there, and we're going to approach it very methodically so that we learn all these steps and we can go through them. So example number 1 is just finding the range, and it's going to give us 2 different pieces of data. It says find the ranges for distributions A and B, and there's a nice little table. So this is the data set for A, and they already calculated our mean and our median for this data set. Remember, mean is like the average. That's where you add up all of them and divide by the number of items. The median is what is the middle value of these different items. And so if you look at A, the mean was 7, the median was 7. If we look at B, the mean was 7, the median was 7. So if we're just looking at the mean and median, we might think, oh, those are very similar data sets. They have a lot in common. But when we go to talk about their range, then we're going to see that it's a little bit different. So for A, I'm going to look at the greatest value in A, and I need to compare that to the least value in A. So the greatest value, luckily these are organized already for us in our tables, going from the least at the top to the greatest at the bottom. So my greatest value in A is 9. My least greatest value is 5. So that means my range is 4. That's really all range is. You take your greatest value minus your least value. Now I'm going to do it with B. My greatest value for B is 13, and my least value for B is 1. So I have a range of 12. Those ranges are very different. B obviously has a wider disbursement of data than A does. A is much more closely together. And so it tells you a little bit different information, because obviously if we look at the mean and median, we could say, oh, these are like pretty much the same sets. But if we look at the individual data points, or we look at the range of the data points, we see that there's a lot more going on. There's a much wider spread in B than there is in A. And so that can either help us draw conclusions or make assumptions on that data set. Now, this data set is very general. We don't know what it's referencing, so we ourselves cannot draw conclusions. But, if those were the test grades or the number of absences or fill in the blank, we could make some conclusions based on the range of our data. And so one thing to note, or one thing that I said, is that even though these 2 disbursements have the same mean and median, the distribution B exhibits 3 times more dispersion or spread than did the distribution A. And so this is why, even though statistics and data are really helpful, they are kind of limiting depending on what we're actually looking at. And so we do have to look at multiple different things in order to help us actually see what's going on. So there was a good table, and I thought it did a good job of helping understand this as well. In your book, Table 10, and this is on page 696 in the textbook. for you that are watching the video, because I don't think you'll get to see this. Over here we have the quizzes. They took 5 quizzes, Gage and Allie did, and it shows what their relative scores were. It shows that their means were the same. Their medians were pretty close. But if we look at the range, they're way off. Gage has much closer quiz scores overall than Allie does, because Allie's got this one outlier here with quiz 4 that she really bombed. And so her range is a lot different. And so I really liked what it said over here. The ranges of the 2 students make it tempting to conclude that Gage is more consistent than Allie. However, Allie is actually more consistent, with the exception of that one score. Because if you look, she's got 27, 27, 28, 27. Those are all within 1 point value of each other. This one quiz throws it completely off. Whereas Gage, he does fluctuate between them. So while the range you would want to conclude, wow, Allie she's really sucked on some of her quizzes if we only looked at that, it can be a little misleading. And so we definitely have to look at the individual data sets before we make an overarching conclusion based on solely the range, because Allie actually is a more consistent quiz taker. This is also why a lot of times, or at least I know in my classes, I'll opt to throw out the lowest test grade because everybody has a bad day. And so why punish you for that one bad day? Let's look at what your overall scores or trends actually are. All right, so that's the table. Let's just minimize that and get that out of the way. Are there any questions on how we find range? Take the highest value, subtract the lowest value. Try not to draw too many conclusions too quickly without actually looking at what your data is stating. That kind of stuff. The rest of this is really going to be spent, or the majority of the rest of this is going to be spent on standard deviation. Standard deviation is based on the deviations of the individual data values from the mean. So what that means is we're going to end up looking at every single data point, and we're going to determine how far off from the mean of the whole is that one data point. If we think about this in terms of like test grades, if you find the mean, that's the average test grade of the class. So then how far off were you from that average? Were you above average by a lot? Were you below average by a little? Where were you in terms of that? And so I made a note that it was 12.2. That's where we did mean, median, and mode. And mean is when you add up all the data, and then you divide by the number of data points. And we did note that with this X bar, that's how we read it. It's X with a little line over it. This is going to become important because the definition of standard deviation and how we find it uses that symbol and that terminology, so I just wanted to refresh you that that was there. So we're going to find the deviations from the mean for all the data points in the following sample. This one only has 5. Try to keep it nice and small to get going. Before you can find the deviations, you have to find the mean. So that's going to be our first step. Find the mean, which is X bar. That's what we have to do first. So in order to do that, we take all the data points. That's 41, 47, 53, and 57. There's 5 data points, so we're going to divide that by 5. Obviously, if you have a lot of data, then this process can take some time. If it's on Pearson and it gives you like 40 pieces of data and it wants you to find the mean, a lot of times that will pop up in an extra window and you are offered the opportunity to use StatCrunch, or it can export it into an Excel spreadsheet for you. You're not required to use either of those. You can do them all manually by hand. That's how I actually do it. But if you want to speed up the process, you can play around with the StatCrunch, or you can use Excel. Excel is nice in terms of finding mean, median, and mode because they have different equations that you can use inside of Excel that will speed up that process. I did post an announcement earlier today that has like a 2-3 minute video on how to actually find mean, median, and mode using Excel if you so want to do that. Again, not required. When it comes to handwritten tests, all of your data sets will be relatively small, so it won't take you a long time to find that information by hand. Okay, so now once we have our mean, this is what we're going to compare all of our other numbers to. So we want to find the deviations from each of our data points. So I kind of like making a little table for these. where we have our data values on top, and then we're going to put our deviations on bottom. So our first data value was 32, 41, 47, 53, 57. Did I run off? Oh, I did not. So then the way we find deviations is we literally are taking our data value, subtracting our deviation. That's it. So 32 take away 46. It's a negative 14. This data value is off by negative 14 points. It's below the average. It's below the mean. 41 is negative 5. 47 is above, so it's going to have a positive value. Positive 7, positive 11. These are the deviations from the mean. How far off are each of our data points from the average or from the mean? And something that's interesting is that when you sum up or add up all of our deviations, they will always be 0, which is kind of just a neat thing. We have negative 14, negative 19, and then if you look here, we have 11, 12, 19. They're always going to add up to 0. So when you're doing deviations, you have to find the mean first, then you're taking your data value, subtract it from the mean, and you go from there. Questions on that one? All right, then let's look at the big baddie. Let's look at standard deviation. It's scary looking. I'm going to walk you step by step through it. It's not as bad as it looks, but it is intimidating to look at because it looks super mathy. But we're going to take it just as it does here with 6 steps. It says, let the sample of n numbers, x1, x2, all the way to xn, have the mean of x bar. Then the sample standard deviation, which we use lowercase s, of the numbers is calculated by the following. And that looks terrifying. Because we've got this symbol that looks weird, that looks weird. There's lots of numbers, lots of letters, lots of blah. So this is called sigma. This means the sum of. So this means we're going to take the sum of all that's in here. Now, what's interesting is all that's in here, this x minus x bar, that's the deviations. That's what we just found. So x minus x bar is deviations from the mean. That's what we just did on the previous problem. So when this says sum of x minus x bar squared, it's saying we're going to take the deviations, we're going to square them, we're going to add them all up. That's what we're going to do on this top part. Down here, n minus 1 means we take the number of elements, the number of data points in our set, and we subtract 1. Then we're going to take the square root of all of that jazz, and that's going to give us our standard deviation. So while this looks really scary, it's not as bad as we think. So what we're going to do is, first thing we're going to do is we're going to calculate the mean. Then we're going to find the deviations from the mean. That's literally what we just did on the last step. We're going to square those deviations. We're going to sum up all the squares. Then we're going to divide them. Then we're going to take the square root. So, looks scary, but we're going to do the 6 steps. We're going to be good. And that's going to give us our standard deviation. Now, this problem I did leave enough room for down here. After that, I will apologize that I did not, and I ended up using the back of a previous sheet, or I used Post-it notes, so you will probably need some more paper. All right, we're going to follow these 6 steps. It says, find the standard deviation of the following sample by using the step-by-step process and then a statistical functions on a calculator. We will not be doing step 2. We are not going to do a calculator method for this. We're going to do it algebraically. So we have this set of data, and the first thing in our step-by-step process is to find the mean. We need to find x bar. So to do that, we're going to add up all of our data and divide by the number of elements that we have. 7 plus 9 plus 18 plus 22 plus 27 plus 29 plus 32 plus 40. Going to add all those suckers up, and we have 1, 2, 3, 4, 5, 6, 7, 8 elements, or 8 pieces of data. And we find that our mean is 23. Step 2 is we're going to find the deviations from the mean. That's what we did on the previous example. And I do like making the little table. You don't have to make the table at all. I just like having that table, so I'm going to do that. Wow, that's really fabulously crooked. But that's okay. So remember, to find the deviations, you're taking the value minus what your mean was. So 7 minus 23 is negative 16. And we do this for every single piece of data. 9 minus 23 is negative 14. Negative 5. Negative 1. 4, 6, 9, and 17. Once your values are over whatever the mean is, obviously you should have positive values for your deviations at that point. Any questions on the first 2 steps? Cool beans. 3, we're going to square these deviations. So honestly, I'm going to just make another row on my table. And I'm going to square them. And notice when you square any of these values, you're always going to get a positive out. Because if you take negative 16 times negative 16, negative times negative will give you a positive. So on step 3, no matter what your deviations were, everything in step 3 should be a positive value. 16 squared is 256, 196, 25, 1, 16, 36, 81, and 289. So we squared all of those. Step 4, sum of the deviations squared. So I'm going to take all of these squared values and I'm going to add them together. 256 plus 196, 25, 1, so on and so forth. We add them all together for step 4. Equals 900. Now, step 5 and step 6, I honestly would probably do all together, but I'm going to show it to you broken up, and then I'm going to tell you why I would do it all together. So step 5 is where you take that sum of your deviations that you squared, and you're going to divide it by the n minus 1. So the sum of the deviations squared, that's what we just did on step 5. That's 900. N minus 1, well, there is 8 elements or 8 data points in our set. So n minus 1 is 7. When you type that into your calculator, you don't get a nice answer. You get 128.57. Here's why I usually will combine steps 5 and 6 together. Because if you use a decimal representation on step 5, and that's what you plug into step 6, you're going to be further off from the actual answer because you already used a rounded answer. If on step 6, which step 6 is where we take the square root of all this, you take the square root of the sum of your deviations squared over n minus 1. Notice we have just built the formula for standard deviation is what we've done through these 6 steps. But at this point, and when I take the square root, I'm not going to put 128.57 in. I'm going to take the square root of the 900 over 7. So really step 5 is a little bit unnecessary, is what I'm saying. I would skip and go straight from 4 to 6. That way I'm not using a rounded amount here, and then I only have one time that I'm going to round for my problem, which is down here. Your problems will be very specific on how many units to round to, so you won't have to be second guessing that. But what the standard deviation tells us is that regardless of what our data value was, for this set, there's a standard deviation of 11.3. That's about how much of a deviation we have overall. So none of the steps are necessarily hard, and the more you do these problems, the quicker the steps start coming. I really like doing the table, at least for the first few steps, because then you're just going to total up the bottom row for step 4, and after that, really, you can jump down to step 6. Lots of computational algebra. Conceptually, I don't think it's, we're not trying to go to the moon here. Questions on any piece of it? Okay, we're going to do a similar process next for frequency distribution. We talked about the frequency. That's how often a piece of data pops up. And we did frequency tables and frequency distributions in 12.2, where we saw how that affected what our averages and our means were. And so now we're going to apply that using our deviations. So now we're going to find the standard deviation of a frequency distribution. It says find the sample standard deviation of the frequency distribution for the table that's given. So we have a value, and then it tells us how often that value pops up in the data set. And so instead of making a whole new table and all that kind of stuff, I'm going to keep extending this table horizontally to plug in all of our pieces of information that we need to define the standard deviation. Because this one deals with frequency, we have to find the value times the frequency first and then build off of that. So I'm going to put one more row down here at the bottom for sums, because we're going to total up some stuff here. If you total up your frequency right here, we have 10, 20, 25. That means there's 25 different data sets or data points in our set here, because 2 pops up 5 times, 3 pops up 8 times, so on and so forth. So we're going to need to know that total, because this is what we're going to have to divide by when we're finding our mean, because there's 25 different pieces of information. But we're not going to just divide these and add 2, 3, 4, and 5 together. We have to take our frequency times our value. Or excuse me, not value. Yeah, frequency times our value. I said it backwards from how I'm writing it. Because we have to know that piece before we can find the mean. So value times frequency, you're literally taking the value times the number times you get it. 2 times 5, 10. 3 times 8, 24. 40 and 10. And then we're going to total those so that we can find the mean. Because before we can find standard deviation, we have to find the mean. The mean is where you take the value frequency column, this 84, and we're going to divide it by the frequency, which gives us our total number of items, which is 25. 3.36. We're going to take it out to 2 decimal places. .36 is the mean or the average value of our value sets. It just saves us using the frequency. We don't have to write out the number 4 times. We don't have to write out the number 3 8 times and so on, and then total those all up in order to do this. So it simplifies our life. So if you remember, the next step after that is we get the deviations from the mean. And so here we're looking at the value versus the average, or versus the mean. So I was just making a little note there. We're not looking at the frequency, we're not looking at the value frequency, we're comparing the value here to the mean that we just got. So we have 2 minus the 3.36, so the deviation is a negative 1.36 here. 3 minus 3.36, negative 0.36. Then we have 0.64, 1.64. We took the mean and subtracted it from the value. What do we do after we find the deviations? What's our next step? We square those deviations, that's right. So we're going to take all these nice decimal values and we're going to square them. We're going to take all of these additional decimal values out to 4. So we have 1.8496, 0.12. That doesn't seem right. I want to test that. That seems weird. 0.36 squared. Okay, that's right. Whoops, I'm just rewriting. 0.4096, 2.6896. That's a 40 on this one. Now, after that, we would typically start summing stuff up. But this one is a little bit different because these deviations don't take into account the frequency that things come up. They don't take into account that we got 2 5 times and so on and so forth. So when you do the standard deviation of a frequency distribution, you're going to have one more piece that you have to do first. And that's where you're going to have to take your deviation squared, that column you just found, and we're going to multiply that by our frequency. So we're going to take 5 times the 1.846 or 96, 8 times this, and so on. And we're going to keep going down. So we're going to take this column times this column to give us this last column. That's the extra step. There's really 2 extra steps because we take the value times the frequency here before we can find the mean, and then we're going to take the deviation squared times the frequency for each of our datas here. After we've done this column where we've taken the deviation squared times the frequency is when we will take the sum of these. Again, this is why I have this last row here. So I would add this one and this one and this one and this one together to give me 19.76. So for standard deviation, remember that's where you have your sum of here. So I'm going to have the 19.76, and I divide by the number of terms minus 1. So I'm going to divide by 24. And I find that standard deviation is 0.91. Yes? So 24 is the number of terms that are in our set minus 1. Standard deviation is the square root of the sum all over n minus 1. So this is our n, is our 25. So we took minus 1 here. Frequency times x minus x bar squared. So it's like we compute a column, then we move on and compute the column. We just kind of keep computing the columns until the very end. So when it comes to, like if you wanted to give your, that's different. Let me go back. Yours isn't colored. But if you wanted to rewrite this in terms of frequency, you could, like if you wanted to have a special one, you would have the sum of the frequency times the x minus x bar squared over the n minus 1. I mean, nothing really changed except that we took the frequency times the deviation from the mean before we took the sum, then we did the division, because we had those 2 extra columns. Are there questions on any of the steps we took to find the standard deviation here of the frequency distribution? All right. So this next one is the one that I did not give you enough space on, and I apologize. Because obviously I didn't. I put the problems in, I was like, oh yeah, that looks like a good amount of space, and that's probably not. I mean, it is if you're writing really small on a sticky note, because I could put both of my sticky notes over there. But it says 2 companies, A and B, sell a 12-ounce jar of instant coffee. 5 jars were each randomly selected from the markets, and the contents are carefully weighed, and the following results. So A, we have these results across the top, and B, we have these results across the bottom. It says find A, which companies provide more coffee in its jars, and B, which company fills its jars more consistently. So this is a very real-world application, because if you are the company, you want to make sure you're filling your jars exactly the same or as close as possible so that you're not losing money in terms of, oops, I overfilled that jar, so that person got a better bang for their buck. And also you want to be consistent, because if you're not consistent, you're going to lose your customers if they find out that they're not getting the right ountage. So what we're going to do is find which companies provide more coffee in its jars. Anybody want to take a guess at what it is we have to find for A, if we're trying to figure out which company provides more coffee in its jars based on the sample field that we have? Knowing that we've learned mean, median, and mode, and we've learned standard deviation, are kind of the big ones. And so far today, we've really only talked about mean and standard deviation. So do you think we have to find the mean of these or the standard deviation to figure out which one provides more coffee? It is going to be the mean. So when you find the mean, remember you're taking all of the data that we have. So like for A, we would add up the amount that's in all of these coffee jars, and then we would divide it by the number of coffee jars by 5 to figure out what's the average amount of coffee in each of these jars. So that tells us what the average would be for A. We do the same thing for B, and then if we compare those 2 values, we can say, based on our data, which is not very much, but based on that, we can say A or B provides, on average, more coffee in their jars, even though both are labeled as 12-ounce jars. So for part A, we're going to find the mean of A and B. And I'm going to label them with these little subscripts so we know which one's which. So for X bar of A, we're looking at what is the average amount of coffee that A puts in theirs. And we're going to round to, it looks like 3 decimal places. And then we're going to do the same thing for B. the mean for B was greater than the mean for A. This tells us that B provides more coffee in their jars on average. Now, as a company, I would want to be more like company A, because if we look at theirs, notice it's 12.008. That's very dang close to 12 ounces even. So they're being more consistent and getting closer to what they're advertising, and thus going to save money in the long run because they're not overfilling their jars with their coffee. So that's what A asks for. Which company provides more coffee? We're going to find the average amount of coffee that's in both of these jars, and we're going to compare them and determine who has the best. B, on the other hand, says which company fills their jars more consistently. Consistently means we're looking at over the spread. We're looking at how good are they at consistently filling jars as close as possible to the 12 ounces. So B is asking us for the standard deviation. So for B, this is where you're out of room, I know. But for B, we're going to find the standard deviation of A and the standard deviation of B. Whichever one is bigger, they're the furthest away from their goal target. You want your standard deviation to be as small as possible so that you're as close to your actual results as you are supposed to be. Now, obviously we have a lot to do for standard deviation, and we get to do it twice in this problem. And just looking at time, we will probably skip a problem at some point in order to, or we'll have to continue on a different lesson, just because these do take some time. Now, for these, I am going to go ahead and do a table. We're going to have to do it for A, and we're going to have to do it for B. So I'm going to start with company A. We're going to have our value. We're going to have our deviation from the mean. We're going to have our deviation squared. And that's pretty much it. So the value was 12.02, 12.08, 11.99, 11.96, 11.99. So the nice thing is two of those columns are going to be exactly the same. Now, the deviation is compared to the average or to the mean that we found for A. X bar A was 12.008. So I'm taking my value minus that. So my deviation would be 0.012, 0.072, negative 0.018, negative 0.048, negative 0.018. Deviation is where you take the value, which is x, minus your average. Then I'm going to square all those bad boys. Ugh. Why did I do so many decimals? I did 1, 2, 3, 4, 5, 6. For some reason, our book had us do 6. Oh, that's why. Notice we have 3 decimals for each of these, so when we square them, they want us to take it out to 6 decimals. I'm going to have to write diagonally. I'm not going to be able to fit them in these little boxes. 0.000144, 0.005184, 0.000324, 0.002304. There's another 0 in there. 4. Obviously, the numbers get kind of crazy, kind of gross. I get it. Again, if you feel more compelled to use Excel, you could use Excel for all of this. Yes, you would have to type in the data values, But then you could type in an equation to do the subtraction here. You could square this. Like, you can do equations for that, but you do have to become a little bit proficient in using Excel, which is not really, we don't have time to go into that. So if you're comfortable with Excel, or if you're comfortable looking up how to use formulas in Excel, you can do some of this that way. I'm just going to do it all longhand because while the numbers are kind of gross, the math isn't all that hard. Because at this point, I would take all of my deviations squared and I would add them together. So I would add this one and this one and this one and this one and this one. And that's going to give me my sum of my deviations squared. .0.00828. And then if you remember, it's the sum of our deviations squared divided by n minus 1. So we're going to take 0.00828 and divide that by 4 because we had 5 jars of peanut butter coffee that we were looking at. So 5 minus 1 is 4. And we find that our standard deviation is 0.0455. So they do a pretty good job of filling their coffee, I feel like. And now we do it all again for B. Because that's for coffee A. Now we get to do coffee B. I'll try and leave coffee A up there too, because we're going to do literally the exact same thing. We have S of B. So we'll have our value, our deviation, deviation squared, and our value was 12.40, 12.21, 12.36, 12.22, 12.27. That's a 7. Now, remember that our mean for B was 12.292. So when we're finding our deviations, we're taking the number of the value and subtracting that. So 0.108 negative 0.082, 0.068, negative 0.072, negative 0.022. Then we're going to square all those bad boys to get our nice, really long decimals. All right, we're going to lose A for a minute. Once we've squared all our deviations, we're going to add all of them up. And then our last step, take the square root of the sum of our deviations that we've squared, and we divide those by the n minus 1. Well, the sum of our deviations was 0.02868. Oh, I didn't put that up there. And then we're dividing that by 4, because again we were looking at 5 jars of coffee, so that'd be 5 minus 1, which is 4. find that the standard deviation is 0.0847. So Company A had a standard deviation of 0.0455. Company B had almost twice that. Not quite, but almost twice the standard deviation. So which company do you think fills their jars more consistently? Is it Company A or Company B? A is more consistent. They're much closer to what they need to be. Since our standard deviation for B was greater than our standard deviation for A, we can say that A fills their jars more consistently. As a consumer, you probably want to buy coffee B because coffee B is giving you a little extra for your money. All of their jars that were randomly sampled had more than the 12 ounces of coffee. Now, obviously, if we were actually doing this for a real company, 5 jars is not a good sample space. We'd need 5,000 jars over multiple different locations and things like that. But that is literally what the whole job description is for like quality assurance and things like that. You're pulling random pieces, random items, and testing them to see if they're right or not. Because if you can catch it early enough, hopefully you can catch it before it's a big problem and you've made a lot of errors on a lot of different products and it's just like one error or like an outlier or something like that is what you're hoping for. All right, are there questions? I mean, theoretically, we've only got 2 problems left. The first problem is very quick. The second problem has a lot going on, and so I'm going to walk you through the second problem mostly for time's sake. But the algebra behind it is not any harder than what we're already doing. So apologies for not giving enough space on the handout. I will be editing that handout. Or I will be printing it single-sided so that you guys have more space. All right, here's a fun theorem, Chebyshev. Chebyshev was a famous mathematician, and he has a fun last name, so I like that he has a theorem after himself. But it says for any set of numbers, regardless of how they are distributed, the fraction, the fraction of them lie within k standard deviations of their mean, where k is greater than 1, is at least 1 minus 1 over k squared. This is going to allow us to find how many items within a data set are within a certain number of deviations. And so it lets you look, are most of the stuff living here or not? Do most of the stuff live outside of my deviations, or do they stay really close? And so we're going to use this. It's straightforward. It really is. There's not a lot to using Chebyshevs, especially for what we're going to be doing with it. So what is the minimum percentage of items in a data set that lie within 3 standard deviations of the mean? Well, that 3 is your k, because k is the number of deviations away from the mean. So if we're looking at any data set, how much of your stuff is going to live within 3 deviations? Well, we're going to take 1 minus 1 over 3 squared. It's 1 over 1/9. Well, that's 8/9. But we want to know percentage, so we're going to actually write that as a decimal. 0.889. So 88.9% of all the items in your data set are going to live within those 3 standard deviations. They're going to live really close, most of your items. You're only going to have about 11% of your items that live outside of those deviations. And so if you're looking at that information and you're looking at at your data, you can really focus in then that the majority fall here, and so I can really just focus on these 3 deviations and I can ignore the outliers. Or if you're trying to bring even more stuff in, you can try and look at your data that way as well. So that's Chebyshev. He was a cool guy. We're not going to do much with him in this class, though. The coefficient of variation says that for any set of data, the coefficient of variation measures the relative dispersion. It is calculated and indicated with this V, and what we do is we take our standard deviation, we divide it by our mean, and we times it by 100%. If you like all of the Greek, I don't remember what all these letters are. That's mu. I don't remember what that one is, though. So if you like Greek letters, you can use those. I'm going to use V equals S over X bar times 100%. And so what this tells us is we're going to be able to just compare the dispersions of our sample sets. So, but as you can see, we have 15 minutes left. We have to find X bar, and we have to find our S for both sets A and B. We literally just did all of that for our last problem, and it takes a little bit of time. So I'm going to show you the process, and then we're going to look at the V's. Because our first thing we would have to do is we have to compare the dispersions of our two sample sets. So we have to find our X bar for A. That's our mean. So we add them all up, divide by the number of elements, and we get our X bar. Then we have to find our standard deviation for A. And so again, I use the table for most of it. I find a value, we find our deviation from the mean. Then we are going to do the deviation squared, and we're going to sum them. So I squared all my deviations, I summed them, I divide by 5 because there were 6 elements to find that the standard deviation of A is 3.124. So if I'm finding the coefficient of variation, I'm going to take that standard deviation, I'm going to divide it by the mean, and then multiply it by 100%. That gives me a 19.3 is my coefficient of variation. Good information, cool, awesome. Then we would do the exact same process for B. Lots of stuff. So again, we find the average. Notice the average for B is much larger, and that's because the data for B is much larger in values. These are very different. The range for A is from 12 to 20, so it only has a range of 8. The range from B is 125 to 193. It has a much larger range. And so these data, I don't know exactly what they're looking at in terms of these data sets, but they're very different. And so we're able to find the average of our B's, find our deviations. We square them, we sum them, we divide them to find our standard deviation is 25.294. So notice the deviation for B is quite substantially larger than our deviation for A. That doesn't necessarily have anything to do with what the data is, the fact that the numbers are larger with our data, because if our numbers had been closer together in our set B, then our standard deviation wouldn't be off as much. But because they're more widely spread, we get that bigger deviation. And so then we're going to take the deviation divided by the average and multiply it by 100% to find that our coefficient of variation is 16.5 for B. So the coefficient of variation doesn't take a lot more math in terms of just finding the standard deviation, because we're just taking the standard deviation divided by the mean, which we already had to do, and then we're multiplying it. But here's what we can draw a little bit of conclusion from. We found that the standard deviation, as I noted for B, is quite a bit larger. And so we know that sample B has a larger dispersion of its data. It covers a wider range of values. But when we look at the V's, we look at this coefficient of variation. Notice A had a bigger coefficient of variation. That means A has a larger relative dispersion. Their numbers are much closer together, but over the average, it actually has a wider dispersion because it doesn't cover quite as much. And so it does tell us different things. So they're definitely different, but we use a lot of the same information to find these different pieces.